Hey everyone, so we've spent some time looking at Riemann sums and integral notation and kind of connecting them and finding the area underneath curves. So now we're going to dive a little bit deeper into connecting Riemann sums to summation notation and integrals and being able to figure out how exactly are they connected and what are we going to be doing with this stuff. So when we find a Riemann sum, we know that we're looking at an estimate. So it could be an overestimate or it could be an underestimate. So we have to sometimes be able to figure out, or a lot of times, be able to figure out whether the Riemann sum we're finding is an over or an underestimate. So we can determine this usually by using key features of the function. When asked, it's always best to draw a picture in order to answer our question. So we're going to do a quick sketch of the graph to be able to figure out exactly what it is that's going on. So we're going to focus first on the right Riemann sum. We have to look at whether the function is increasing or decreasing. So this information is usually given in the instructions, which means a lot of times you have to actually read the problem. So if we have a function that's increasing, let's say we've got our function here, right? And we've got a function that's increasing like this. If I want to use a right Riemann sum, I need to think about what that would actually look like. So if I pick an endpoint right here, and I draw it over to my left endpoint, there's one rectangle. And then if I do another one right here, here's another rectangle. And I can maybe draw one more. And my Riemann sum is going to be the area of these red rectangles that I just drew in. We can clearly see that that's going above this curve that I just drew, which means if you have an increasing function and you're doing a right Riemann sum, it's going to be an overestimate. Let's look at what happens when we have a function that is decreasing and we do a right Riemann sum. So again, let's draw a quick sketch of what's happening here. And we're going to have a graph that comes down maybe like this. So let's go ahead and do a right Riemann sum there. So now if I come over and I make a point right there and I draw to the left, there's one rectangle. Starting at the right end point and drawing over, there's another. And I can draw maybe one more. These aren't the best rectangles, but y'all know what I mean. So here's the area that we're actually finding. And we can see, based on where that curve is, these rectangles are all underneath that, which means this is going to give us an underestimate. Okay, let's look at a left Riemann sum. So again, we're going to look at whether the function is increasing or decreasing. Again, usually given in the instructions. So now let's look at a function that's increasing. So I'm actually going to draw the same function, or similar anyway. Got this function going up that's increasing. And now we're going to do a left Riemann sum. So that means I'm going to start here and go over and draw my rectangle. And then start at my left endpoint, go over, and draw my rectangle. So it's a little bit hard to see at first, but the more that we do it, the more we would be able to see that these green rectangles here are all underneath the curve, which means if we have a left Riemann sum with an increasing function, that's going to be an underestimate. For a decreasing function then, there's my decreasing function, and if I start to look at my left endpoints, so let's say I'm going to pick an endpoint right here, go over and come down, left endpoint, go over and come down, and do it again. I can see that those green rectangles, that first one, it's a little bit hard to see. Sorry, I should have drawn a better curve there. But all of those green rectangles are now going above my purple curve, which means if I'm looking at the area under the purple curve, I've now gone over it, so it's an overestimate. But you can see how these pictures clearly help us decide whether it's an over or underestimate. Don't try to memorize anything, just draw yourself a quick picture and draw a couple rectangles to be able to make that decision. The last type we've got our trapezoidal sum. So now we need to look at whether the function is concave up or concave down. Because that'll help us determine whether the trapezoidal sum is an over or an underestimate. So if I think about a function that is concave up, that's going to be something that kind of looks like that. So maybe I can draw a parabola that's up here like this. So there's my function. And I'm going to draw a trapezoidal sum. This one's a little bit harder to see. But for a trapezoid, I know that I'm going to draw in both of my points there. Here's one point, here's the other, and I'm going to connect them to make a trapezoid. And then here's one point, here's another, and I connect it. It's a little hard to see as I'm going here right at the middle. But once I start to come up on this side, I can see that they start to go above the actual graph, which means this one is going to be an overestimate. So if I have a trapezoidal sum and I have a function that is concave up, I'm going to get an overestimate. Again, I know it's a little hard to see. The concave down one is actually easier to see. So let me show you that one real quick. I have a function that's concave down. So let's say it looks like this. And now I'm going to make my trapezoids. So here's one, here's the other, and I can see that that line connecting them is underneath my actual function. Not the best picture, but hopefully you guys kind of get the idea there, that now if it's concave down, it's going to end up being an underestimate. And I can show you guys some better graphs in class. I'll actually pull some up on Desmos and show you exactly what it'll look like so that you can see a clearer picture of it. So let's actually see what this would look like in an AP question. For this one, we can actually use our calculator. It even tells us right here, you may use a calculator. So water is being removed from a tank at a rate modeled by R of T in liters per hour, where R is differentiable and decreasing on the interval from 0 to 8. So that's going to be important because we're going to be using a left Riemann sum here. I jumped ahead, sorry. But I jumped ahead and noticed we're doing a right Riemann sum. So the fact that this function is decreasing is going to be important because my bet is they're going to ask us if we have an over or underestimate. So here's all these values. Use a left Riemann sum with 4 subintervals indicated by the table, so that we can figure out the total amount of water removed from the tank during the 8 hours. So if I'm going to do a left Riemann sum, let's see, I'm doing from 0 to 1, I'm doing from 1 to 3, from 3 to 6, and from 6 to 8. I'm doing a left Riemann sum, which means I need my left endpoint so that I can figure out what I'm doing here. So let's see, my left endpoint here is going to be 1340. My left endpoint here is going to be 1190. 950 and 740. And then I know I'm going to need the width of my interval. So from 0 to 1 I know is 1. From 1 to 3 is 2. From 3 to 6 is 3. And from 6 to 8 is 2. So everything I just wrote in purple is the width of the rectangles. The green is that left height, that left endpoint. and I know I need to add those quantities together in order to get my estimate. So grab your calculators, do it real fast. Let's see, 1340, 1190, 950, 740. All right, I got 8,050. So let's think back to what we were actually doing. Estimate the total amount of water removed from the tank in the 8 hours. So liters. 8,050 liters were removed from the tank. During the 8 hours. Okay, so let's see then. The next part says, is this an overestimate or an underestimate? Give a reason for your answer. Well, we know that this function was decreasing. They told us that here. Plus, if we look at these values, we can see that the rate there is clearly decreasing. So if our function is decreasing, and we're using a left Riemann sum, well, let's think about what that would look like then if we were to pick some left endpoints. That'd be here and go over here. It'd be here and go over. So we've got a left Riemann sum for a decreasing function. It means that this is going to be an overestimate. So let's see. This is an overestimate. Because r of t is a decreasing function, and we used, what did we use? Left Riemann. Sorry, I know I didn't leave myself enough room there to really write it. Hopefully you guys left yourselves a little bit more room. So we got 8,050 liters was removed. This is an overestimate because r of t is decreasing, and we used a left Riemann sum. So if we look at our picture here, we can clearly see that the area we found is over the actual function. Okay, I am going to skip question 2, and we can talk about it in class. I want to jump down to this big idea here. So we're looking at these Riemann sums, right? Which means we're adding up together all the areas underneath the curve. And the big idea here that we need to talk about is that if we add enough of the rectangles together, we get an exact answer. Everything we were adding together with those rectangles was just an estimate, and sometimes it was over, sometimes it was under. The more rectangles that we add together, so the smaller that we actually make the subintervals, the more exact that we can get to. So we want to talk about how to actually achieve that. So take a look here. This is our summation notation. This should hopefully look at least a little familiar to you. You should have seen it before. This big giant E that's here is called a sigma. And when we see a sigma, we know that we're finding a sum. So if we're adding all the rectangles together, we're finding a sum, right? And it's not just that we're adding a bunch of rectangles together. If you look here, we're saying that n should approach infinity, and n is the number of rectangles, which means we want an infinite number of rectangles inside of this interval that we're looking at. So if I can make an infinite number of rectangles, which means that their width is going to be super, super small to be able to fit an infinite number on this interval, then I'd be able to get the exact area that I'm actually looking for. So another part of this should look super familiar to you. You should be able to pick out that this f of x that's written here is actually just our y values. It's the height of the rectangles that we use when we're finding the actual area. Delta x that's written here, we know that delta x stands for the change in x. So this is going to be the base of our rectangles. And since we're doing an infinite number of rectangles, we're trying to make this base as small as possible. So it's going to be super, super small numbers in order to be able to make an infinite number of rectangles on this interval. And that's the other part that I want to actually point out to you, is we're doing this limit notation, but it's on this interval from a to b. So we know that if we've got a, that's our starting x value. So we start at x equals a. And b is where we end, so we stop at x equals b. Now what we need to be able to do is we need to be able to go from summation notation to integral notation. These two things are actually going to be equivalent to each other. So this limit notation that we just kind of dissected over here and this integral that we're going to write are going to be equivalent to each other. So we know if we're doing an integral that we need an actual integral symbol, and we need our bounds of integration, which happen to be the endpoints on our interval. So we're going to start at a and we're going to end at b. And then we need our actual function f of x. And remember, we talked about always closing the actual integral. So in order to close the integral, we need to have something here to actually close it. That's going to be our dx. Dx and delta x are actually the same thing. They represent the same part. We're looking at the base there. So we need our delta x to close out our integral. Let's look at what this actually looks like in an example. So express each of the following limits as integrals. We've got our infinite number of rectangles here. Here's our function inside, and here's our delta x. So we know we need the integral. And we know that our integral needs a start and a stop. So when we look, we're going on the interval from -1 to 3. That means that's our a and that's our b. So it's the integral from -1 to 3. Now we need our function. If you take a look though, that function looks a little funny. I don't know if it looks funny to you guys or not, but I'm going to put some parentheses here. Look at this function. We've got m sub k here and m sub k here. Really what this means is we're looking at the specific x values that we're adding together. So this could be something like we were taking the midpoints. So really, when we switch to integral notation, we're going to get rid of that weird m sub x, or m sub k, excuse me, and we're just going to put in an x. Which means that this function is really just 3x squared minus 3x plus 5. So we're going to take out that weird notation there and just simply put in x because we're talking about f of x. And then we need to close out our integral and make sure we show that we've got a dx at the end. For number 2, it's very similar. We're going to make our integral symbol. We're going on the interval from 0 to 1. If we take a look at our function, now it's a little different. We've got this square root of 4 minus, and we've got this weird c sub k squared. That c sub k, again, just means the specific x values that we're adding up, and so we're going to replace it with an x. So it's going to be x squared, and then we close out our integral with a dx. Alright, hopefully you took your notes, wrote down any questions that you had so that you can ask in class. I will see you in class for some practice. Thanks for watching.